Welcome, and thank you for your interest in Clearfly's SIP Troubleshooting for Technicians presentation. My name is Ken Mix, and I'm a network engineer with Clearfly Communications, a provider of voice and data services throughout the lower 48 states. This presentation is technical in nature and is designed to help inform and expedite the troubleshooting process for folks who handle the install, operations, and support of Clearfly's SIP service. All voice services Clearfly provides are signaled via SIP. Even if we provide an AdTran gateway to hand off legacy POTS, PRI, or CAS-T1 services to a phone system, the upstream connection from that gateway to Clearfly's network is SIP. These gateways serve an ever-decreasing percentage of our customer base now, though, and the vast majority of our services are provided via direct SIP trunks from our voice core to customer phone systems. As such, we've managed to gain a fair amount of experience in-house in troubleshooting different problems that may arise during provisioning of new SIP services, or intermittent issues that may pop up after service has been installed and running for a while. The goal of this presentation is to share some of our experience with our partners, as well as some of the lessons learned and the troubleshooting methodologies that have evolved at Clearfly to help us expedite the diagnosis of problems and ensure speedy resolution. And, while we hope that some or all of you will find parts of this presentation useful, we're also 100% confident that we've missed or omitted tips or tricks that you folks have gathered over time. We'd like to be able to evolve this presentation based upon your feedback and are open to any suggestions, ideas, or additions that you can offer us. For the rest of this presentation, I'm going to assume a base level of knowledge, and that is that the folks watching know what an IP network is and the basics of how IP packets flow, and that everybody here knows what SIP is and what it's used for. I'm also going to assume at least a passing familiarity with the industry standard terms listed here. Also, I reference bits and pieces of several packet capture files throughout this presentation. Copies of these packet captures are available next to the presentation link in the training section of the Clearfly portal. So, diving into this, we'll take a quick look at a very basic 100,000-foot view of the evolution of phone services, at least from Clearfly's perspective as it pertains to this presentation. The first logical question is, what makes SIP so special? The diagrams don't look that different. Sure, there may be some nuance, but a lot of folks out there have had decades of experience installing and troubleshooting phone systems of what we now call, quote-unquote, legacy phone services. Doesn't this experience translate directly over to VoIP in general, and SIP in particular? And, unfortunately, we found the answer to be not really. It's always helpful to have experience troubleshooting technical issues. That's experience that'll hold up pretty well across any discipline. The problem, though, is that any kind of in-depth troubleshooting requires a good foundation, or, to mix metaphors, a deep enough well to draw from. Otherwise, guesswork and assumption are going to draw out problems that a well-founded technician would be able to work through logically and resolve quickly. Compared to the legacy private switch telephone network, or the PSTN, where things have been developed over the period of a century and have evolved in a fairly stable fashion, a SIP stack that has been around for a decade is considered to be an old-timer. And instead of one all-knowing, all-controlling Ma Bell, every vendor has developed a SIP stack based upon their own interpretation of the RFCs. Now, combine the variations in different vendor SIP implementations with the infinite number of potential IP network configurations, devices, and vendors, and things start to look pretty chaotic. Considering the potential problems that are sure to surface when all these elements are mixed together is enough to make a guy long for the good old days when you could just plug a butt set into a 66 block and definitively say, okay, there's your problem. However, having said all that, it's not nearly as bad as it sounds. 10 years ago was a different story, but a decade is a long time for people to fix bugs, write dozens of RFCs, and agree on conventions and best practices. Interoperability get-togethers like the SIP Forum's annual SIPit event go a long way towards ensuring interoperability between different SIP stacks by allowing them to test back-to-back in a controlled environment. Organizations like the SIP Forum also provide venues for industry stakeholders to get together and agree on best practices. So despite the mishmash I previously described, most of the problems you'll run into will fall into a few easily solvable categories. Nothing here is magic, and while there may be some outliers or some problems that fall outside of this common set, they're going to be the extreme exception. If you haven't already, you're going to find that on the SIP trunking side of the house, problems generally fall into two large buckets: signaling, related to SIP, or media, related to RTP. Signaling issues are issues related to call setup, call progress, and call termination. Media issues are issues related to audio quality, one-way audio, call setting up without audio, etc. I'm going to group QoS in with media issues since QoS issues are almost always experienced as poor or choppy or echoing audio. Severe network congestion can lead to signaling issues, But in those instances, the actual SIP signaling is usually going to be the least of your problems. These are broad categorizations, of course. Many media issues are, in fact, due to signaling problems, but classification is still a useful exercise to narrow down the specific symptoms you may be trying to troubleshoot. Before you can troubleshoot or even categorize a problem, however, and I can't emphasize this enough, good data collection is a must. Those of you who've called into Clearfly support lines are familiar with the question, do you have a call example? This isn't an attempt by our support folks to brush off a problem. It is simply necessary for us to even begin troubleshooting, and it should be necessary for you too. Aside from the fact that Clearfly processes tens of thousands of calls an hour, and defining your call without a good example is improbable, how can you begin to analyze a problem when you have no data? A good call example always consists of the following: a calling number, a called number, a date and time, preferably with time zone, and the user's experience. What happened on the call, and be as specific as possible. For example, by call drop, do you mean that the call disconnected, or are you simply suddenly unable to hear the person on the other end, or vice versa? If the audio was garbled, which party in the call could hear the garbling? Was the other direction fine? Also take time to step back from the problem call. Following questions can provide useful clues. Have you had any other phone problems? And if so, how recently? If there have been other recent problems, are they the same types of problems? Are there any call examples for the other problem calls? If this has happened more than once, what is the frequency? Is the issue intermittent or regularly recurring? And is the problem repeatable? I know these all sound like extremely basic questions, but that's really the point. There's often a tendency for experienced techs to skip the basics, and I can't tell you how many hours I've seen wasted, and frankly wasted myself, chasing down a blind alley when often a more thorough data collection would have led efforts in a completely different and usually more fruitful direction. Since call examples are so important, we provide an easy way to add them in the Clearfly portal. There's a button within the ticket view specifically for adding call examples, and we found that having a set form helps reinforce good troubleshooting practices by ensuring consistent data collection, which often leads to quicker ticket resolution. Note that only the fields with red asterisks by them are required to actually submit the form. Call details are the first and most basic type of data to help you troubleshoot an issue, but there are other places you can look as well. Many phone systems have the ability to maintain very detailed logs, up to and including signaling packet data. If you can't find diagnostics information in the manual, it's likely worth checking with the manufacturer to see what's available. Depending on the type of issue, router or firewall logs may, albeit rarely, prove useful. Again, check with the manual or the manufacturer, or, depending upon the popularity of your device, a quick Google search may get you what you need. Just an obligatory note of caution here. Only download firmware, admin software, etc. directly from the manufacturer's website. A compromised router makes it for an ideal foothold into an otherwise secure network. Finally, combined with call examples, packet captures are the single most useful type of data that can be collected when working towards resolution of a problem. Packet captures can be obtained at many points in the network and from many devices. Some phone systems are capable of capturing signaling or both signaling and media packets. Some routers or firewalls offer packet capture capabilities. Some managed switches have the ability to set up mirror or monitor or span ports, but the best and most reliable source for packet capture data is via a dumb network hub or a dedicated network tap appliance. Hubs and taps are more reliable than other methods because you're getting the layer 2 data directly from the network. With the phone system, router, or firewall, the packets you are capturing are packets that have possibly already been manipulated, and thus don't necessarily provide a clear, accurate picture of what is happening on your network. This is less likely to be a problem with the mirrored switch port, but is still something that should be considered. Additionally, mirror or monitor configuration varies by vendor, and capabilities are nowhere near universal. Reliable, dumb hubs used to cost a dime a dozen and were laying around everywhere, but they're not trivial to come by these days, so your best bet for obtaining packet captures is likely going to be a network tap. For both lab and field scenarios, we use Dualcomm's DCGS 2005 Ethernet taps. They're gig capable, have the ability to monitor PoE ports, and are basically plug and play. There are other models by Dualcomm and other manufacturers that work well and may be less expensive than the DCGS 2005 $170 retail price, but the sturdy metal case and the fact that it can be powered via USB from a field tech's laptop have made it ideal for our use cases. In the past, taps were not affordable options unless dealing with twisted pair copper, but many manufacturers now make fiber Ethernet taps that won't break the bank. Another important consideration is, where should you acquire a packet capture? Unfortunately, there's no easy, one-size-fits-all answer for this. It largely depends upon the type of problem you are trying to solve and where you are at with your troubleshooting. If a router or firewall's NAT or ALG is suspected, it may sometimes be necessary to capture both inside and outside of the firewall at the same time. In these instances, if resources are limited or if the WAN type precludes testing outside of the router or firewall, you can always schedule a coordinated capture with Clearfly. An example is a T1 or FiOS handoff, where installing an Ethernet tap is impractical or impossible. During these coordinated captures, Clearfly will set up a packet capture on the outside of our session border controller, or SBC, while you set up your internal capture. We can then provide you with the capture, or vice versa, depending upon which direction the troubleshooting takes you. Once you've determined how and where to acquire your capture, you'll need software to actually capture the packets and save them to disk. Although there are many different options available, Clearfly uses and recommends Wireshark. Wireshark is open source, supports Windows, Mac, and Linux, and is available via free download from wireshark.org. One note here is that Wireshark is still working through quite a few issues after bumping up to their 2.x release family. While the latest version is flawless for actually capturing packets, I've upgraded and downgraded many times and find that the latest 1x release, 1.12.13 as of this recording, is still far less buggy when it comes to analyzing your VoIP traffic via the built-in tools. All previous versions of Wireshark are available from the mirrors listed on their download page if you're feeling adventurous or run into odd bugs that hamper your productivity. Since Wireshark is such an important and useful tool for troubleshooting VoIP problems, we're going to spend a couple of slides dipping our toes into the water before we dive into specific problems. Wireshark has a lot of built-in functionality that takes most of the work out of analyzing VoIP packet captures. Full tutorials are available all over the internet, including a wide selection on the Wireshark website, and there are even some print books available that are fairly recent and pretty useful, whether you're a Wireshark newbie or veteran. Clearfly also has a knowledge base article on our website at clearfly.net that walks through some of the features that I'm about to cover, basically those that are particularly relevant to VoIP troubleshooting. When you first fire up a packet capture with default settings, it's probably going to look pretty noisy, depending upon where you're connected to the network, so the first thing you'll likely need to use is the display filter. On busy networks, there can be a lot of extraneous information contained within a packet capture, and a display filter is a great way to ensure that you only see what's relevant to you. When troubleshooting SIP voice calls, you'll probably find one of your favorites to be SIP, which just displays the signaling, or even SIP or RTP, which displays both your signaling and your media. So that cleans up the display a bit, but you can get quite a bit deeper and use the display filter as an integral part of your troubleshooting toolkit. For example, to show only SIP invites, you can type sip.method, and you can filter by any method, but for this one we'll do sip.method equals invite. So that shows you only the invites within this packet capture file. If you're troubleshooting media issues and you only want to see packets with an SDP in them, you can simply type SDP, which is a very useful filter. As you work more in Wireshark, you'll likely build up a go-to repertoire. Another nifty time-saving feature is the ability to define filters based upon various elements within the packet. For example, you can expand out the headers in a particular SIP packet, right-click on the SIP call ID, and actually apply that as a filter. This will show you all the SIP packets within this particular SIP dialog. And while being able to display a list of relevant packets is useful, Wireshark takes things a step further with their built-in VoIP and RTP analysis tools. For example, you can find all calls via the VoIP calls dissector by clicking VoIP calls under the telephony menu. This will actually parse the file and find all calls in the capture for you. Of particular note for operational text is the state column that displays the status for each call. This output continues to update in real time during a capture, so the state is a good way to ensure that you have all the packets for an interesting call, or whether or not a call is still in progress. You can also select a particular call on this list, click the flow button, and you have a SIP ladder diagram. Ladder diagrams are an excellent way to quickly visualize a call's packet flow. Also note that by clicking on a row in the ladder diagram, it'll take you directly to that SIP packet in the main Wireshark packet display. This can be a real time saver. We can also explore another handy telephony troubleshooting feature by clicking on a call in the VoIP calls window and selecting the player button. The RTP player can actually decode and play back audio from a call. G711 is supported by default, but G729 can be decoded using some third-party tools. A full tutorial for these add-ons is available at wireshark.org. A SIP call's media consists of two distinct unidirectional packet flows, which you can see in this window. Also note the detailed information available for each RTP stream. The drops by jitter buff stat can be an immediate indicator of audio problems due to jitter, which is likely caused by a lack of packet prioritization, or QoS, on the network. If playing the audio isn't enough, more detailed RTP analysis can be performed by clicking Telephony, RTP, Show All Streams from the main Wireshark window. Selecting an RTP stream and, optionally, its reverse stream, and then by clicking Analyze, it'll take you to a stream analysis window that tells you everything you need to know about an RTP stream, particularly about jitter and loss. Since RTP media is unidirectional, statistics may be vastly different in one direction versus another. If a customer is reporting that their calls are garbled in one direction, this is a good way to determine whether the issue is QoS related or whether something is happening before the audio is packetized. Okay, we've covered the basics of Wireshark, but before we dive into the next section, I want to quickly review RFC 1918 and the concept of private versus public IP addresses, as it will come up later in the presentation. There are blocks of IP addresses, also known as private IP addresses, that were set aside in RFC 1918 and 1996 when it started to become apparent that the Internet's original addressing model wouldn't keep up with the already explosive demand for Internet addresses. In the original model, every computer connected to the Internet simply had a globally unique, globally routable IP address assigned to it. Bear in mind that this was long before everything from your refrigerator to your car was connected to an IP network. Basically, RFC 1918 introduced the concept of private and public IP addresses. Public IP addresses would be globally routable and globally unique, whereas private addresses were intended to be addresses that were not globally routable and could thus be reused within different routing domains without worrying about reachability problems due to IP address overlaps. For example, if the IP of the PC on your LAN is 216.58.217.14 and you try reaching google.com that also resolves to that IP address, obviously your PC will loop the packets back to itself instead of directing them to the default gateway, which it would do if an IP address were in a different subnet. Thus, the packet will never reach the Internet, and your PC, as well as any other PC in a subnet that overlaps with Google's IP, would be unable to reach Google. If, instead, the PC had an RFC 1918 address on it, for example 10.1.1.100, traffic to Google's IP would flow to the default gateway, would be network address translated, or NATed, to a globally unique public IP address, and would then route hop by hop across the Internet to Google. RFC 1918 addresses are for local use only, and no host on the Internet should ever have an RFC 1918 address assigned to it. So as long as the PC has an RFC 1918 address assigned to it, overlap with the rest of the world can be avoided. One final note on private IPs. Traffic to and from the subnets defined in RFC 1918 are typically blocked at the edge of an ISP's network, or are black-holed within the ISP's routing tables. If you ever see an IP in one of these ranges in an SDP that was observed outside of a firewall, one-way audio issues are possible. And on that note, probably the most common issue we see on new deployments is one-way audio. Usually, the PSTN side of a call can hear audio, but the person at the customer site cannot, so we'll dive into that now. One-way audio issues are typically caused by one of the following problems. First, the phone system is behind NAT, but the NAT device's SIP ALG does not exist or is disabled, and there are no static translations to the PBX's RTP port range. A fix for this is to enable the ALG or add static translations through the device for the relevant SIP and RTP ports. And second, the phone system is behind NAT, but the IP in the SDP is not being translated. There are a couple fixes for this. One, add the public IP address to the phone system, which is often found in a PBX's NAT or SBC settings. Fix 2 would be to configure or enable a router or firewall SIP ALG. ALG stands for Application Layer Gateway. This is the least preferable from Clearfly's perspective. For the most stable service, Clearfly strongly recommends that if a phone system is behind a NAT device and supports configuration of a public IP for NAT traversal, then the SIP ALG should be disabled if it exists, and the relevant port should be statically translated through the device. Specifically, this includes UDP 5060 for SIP signaling, unless you're using another port, and a range of RTP ports to be determined by your phone system vendor, and which may or may not be configurable. By disabling the ALG, you are taking another software stack out of the equation that could be making changes to your signaling packets. This minimizes the chance of problems down the line when router or firewall software is upgraded, or when configuration changes are made. Before the next couple of slides, I'd like to spend a minute reviewing SIP's media negotiation mechanism. It's important to understand that media parameters on a SIP call are negotiated as part of the setup of every single call, and media parameters may even be renegotiated one or more times during the call. For instance, when a fax call renegotiates to T.38 from G.711. Basically, each side sends a session description protocol, or SDP body, within a SIP request or response. This SDP body includes information such as codec preferences and the IP and port the other side should send audio to. I want to emphasize this last part, as I think a firm understanding of this one piece will likely be a huge help in troubleshooting audio issues. Since RTP streams are separate, unidirectional UDP flows for each audio direction, the IP and port settings in an SDP from, say, Clearfly's switch have no bearing on the IP and port that the remote phone system will specify, and vice versa. In this example, the phone system sends an invite with an SDP that specifies G.711 MULA and G.729, in that order, as the codecs that are supported, a connection IP of 208.85.60.106, and a connection port of 10012. This is the IP and port that the phone system is asking us to send RTP packets to. Clearfly then responds with a 183 session progress response that contains our SDP. G.711 MULA is acceptable, so that is the only codec we include in our message. Our connection IP in this example is 208.85.62.102, and Clearfly's standard range of RTP ports is 20,000 through 29,999. Our port is in that range, in this case 25252, so we want the phone system to send RTP traffic to 208.85.62.102, port 25252. Not to sound like a broken record here, but the key really is understanding that RTP flows are unidirectional and unrelated. Since the RTP flows are unidirectional, it doesn't matter to us what these values are. Each system should send audio to whatever port IP combination is specified in the SDP. If you are getting one-way audio and are fairly confident in your NAT configuration or ALG behavior, your problems are likely caused by a private IP address in the SDP. Let's walk through a quick example so that you can easily identify this issue if you run across it. Obviously, you need a packet capture outside of your router or firewall, or a capture from Clearfly in order to properly diagnose this problem. Private IP addresses on the inside of a NAT device are perfectly normal. Note that the SDP in the invite has a connection IP address of 192.168.0.106. This is the IP address Clearfly will send audio to. As we learned previously, RFC 1918 addresses are not globally routable, so these RTP packets will be lost on the internet and will never reach the phone system. On the same call, Clearfly sent 208.85.62.116 and 21678 in our SDP. When the phone system sends audio to this port and IP combination, the person on the PSTN or Clearfly end of the line will hear audio. Thus, we now have a one-way audio situation. Over the last several years, as we've updated our SBC, the software has become progressively better at handling SDP issues due to NAT problems or misconfiguration. As a result, there are some scenarios in which two-way audio will work even with private IP addresses in the SDP. For registered SIP trunks detected as behind NAT, Clearfly's SBC will utilize intelligent media latching to determine where to send media. Basically, this means that the SBC will dynamically determine where Clearfly should send RTP packets to, based upon the information in the SDP, as well as the IP and port it is receiving RTP packets from, for each call. For static SIP trunks and registered SIP trunks not detected as behind NAT, our SBC will still attempt basic latching if media comes from an IP not defined in the SDP. This can result in two-way audio working, even when it probably shouldn't. To be honest, while the advanced media latching behavior helps a lot of people get off the ground with less pain, from a long-term perspective, I prefer stricter media policies that would require folks to take the time to properly configure systems from the beginning instead of waiting for problems to surface down the road. But, in reality, most call flows are simple enough that a lot of systems will never experience ill effects from this latching behavior. Now we're going to run through a quick overview of some aspects of SIP signaling and then take a look at some other common problems Clearfly helps our partners troubleshoot. For the next couple of scenarios, I need to walk through some elements of a SIP session for you and show how SIP dialogues and transactions fit together within a session. First of all, a SIP dialogue is basically one leg of a phone call. For example, the call between a customer's PBX and Clearfly's SBC. It is identified by a SIP call ID and the local and remote tags on the from and to headers within a SIP message. A dialogue is established by an invite message and can contain one or more transactions. For those unfamiliar with basic SIP flows, a SIP invite is basically the first message you'll see when a SIP endpoint's trying to establish a new call. Within a dialogue are individual SIP transactions. A transaction is basically a request and any responses to that request. A transaction may belong to only one dialogue, is identified by the branch parameter, and you can track a transaction through an incrementing CSEC value, which you'll see in subsequent slides. Of importance to upcoming slides is the fact that a transaction does not include an ACK if it was in response to a 2XX response, or a PRAC message in response to a 1XX. Also, all responses within the first transaction in a dialogue are simply sent to the IP that the request was received from to initiate the dialogue. But, and this is very important, any packets outside of the first transaction within a dialogue will follow the host part information, so basically the IP or domain name, that's in the contact URI of each SIP packet. So let's look at a quick example. Here we have a full dialogue which contains 4 separate transactions. The dialogue and first transaction are initiated by the invite message. This is the red transaction. Subsequent messages in this transaction are sent to the address in the top via header. Messages within this transaction can be identified by the branch parameter in the via header and the CSEC value. Note that the initial transaction does not include the ACK in response to the 200 OK. The ACK, which is the green line, is by itself, as are the PRAC and its 200 OK, which constitute their own transaction and are represented in blue. The BY request, which is what ends the call, and its 200 OK response make up the final transaction and are represented by the orange lines. The first message in the next new transaction, in this case the PRAC, are sent to the contact address from the previous transaction. This transaction is fine, since the IP in the contact header is the correct public IP address. However, the next 3 issues we'll look at are all caused by a private IP address in the contact header. These next few slides are only relevant for static SIP trunks, as the contact headers are dynamically determined by Clearfly's SBC for registered SIP trunks. The first scenario we'll look at is calls dropping after 15 minutes. There is a standard SIP session timer that most implementations default to 30 minutes. A SIP endpoint will try to refresh a session at 1/2 the session timer, so 15 minutes. It does this by sending a reinvite within the dialogue. Since this is a new request, it is a new transaction and the packets are sent to the IP in the last contact header, in this case 192.168.0.106. Eventually the call is dropped when the endpoint that sends the reinvite does not receive a response. Wireshark SIP ladder diagrams are incredibly useful for diagnosing these types of issues, as you can clearly see that there is signaling going to the private IP address, which is something you should never see outside of a router or firewall. There are a couple possible fixes for this scenario, which will be the same for all issues related to private IPs in the contact header. Number 1, you can add your public IP address to your phone system config if supported. This can often be found in the NAT settings or, for some systems, the built-in SBC or SIP manipulation configurations. Number 2, you can configure or enable the SIP ALG in your router or firewall so the private IPs are rewritten with your public IP. As we mentioned previously, this should be a last resort if nothing else works. Our second scenario deals with calls that fail to set up, or seem to set up, but then drop after 20 to 40 seconds. Since a PRAC, or provisional acknowledgement, is not part of a transaction, it begins a new transaction within the SIP dialog, and so it is sent to the IP in the invite's contact header. Early media will often establish on these calls, but without a response to the PRAC, the call will eventually be dropped by the endpoint that sent the PRAC. Early media is any media that is transmitted before a call is actually established. A good example of this is when you call a cell phone and hear music or some other custom ringtone. There are also some voice trees at big answering centers that take advantage of this to start playing a greeting immediately instead of waiting for a call to finish setting up. In these scenarios, you're hearing audio from the far end before the call establishes, so any problem in call setup can seem like a call was working, but then dropped. And our third and final private contact IP scenario involves calls that don't end properly or appear to be hung on the phone system. Since a buy is part of a new transaction, when the call is ended by the PSTN side of a call, the buy request that typically ends a SIP dialog never reaches the customer's phone system, so the call will basically be hung on the phone system. Newer, more mature software stacks are better at cleaning up these zombie sessions, but on older phone systems, it's not uncommon to see the system eventually just busy out because of too many hung sessions that it thinks are still active calls. The last few slides dealt with contact header problems, which only apply in the case of static SIP trunks. For the next few slides, we're going to discuss common turn-up issues covering both static and registered SIP trunks. For static trunks, if no inbound or outbound calls are working after a new install, the very first thing to do is verify that you gave us the correct public IP address and that we've loaded it properly in our systems. This is something that can be verified via the Clearfly portal. If everything looks good in the portal, the next step is to verify that the system is actually sending from the expected public IP address. It's not uncommon for customers to give partners the wrong IP address or for them to have a funky router config that may be natting things differently than you'd expect. This is especially true for customers that have dual WAN setups. A capture outside of the router or firewall can be useful to figure out how your packets are being manipulated before they're sent to the internet. If outbound calls are working, but inbound aren't, it's likely that your system isn't responding to options messages. An options message is simply a SIP message that Clearfly's switch sends out periodically to determine if a SIP stack is still alive or if unavailable forwards should be kicking in. If a system's not responding to options messages, this too is something that can be verified in the Clearfly portal, which we'll see in more detail shortly. If the portal shows that your system isn't responding to options messages, the next step should be to verify any port translations if the phone system is behind NAT. Either way, a capture on a WAN interface of a router or firewall may be useful for determining if packets from Clearfly are even reaching your network. If they're not, and you've verified that the IP address in the portal is correct, there's a good chance the ISP is blocking SIP traffic. This used to be very common on cable modems, but has been less of an issue in recent years. If you are seeing the packets reach the WAN, the next step is to capture between your phone system and the router or firewall to ensure that your SIP packets are actually making it through the device, which will tell you if you need to work on the router or your phone system. For registered trunks, if no inbound or outbound calls are working after a new registered trunk install, the very first thing is to verify whether or not your system is registered. Registration status, as well as your registration username and password, can be verified via the Clearfly portal. If your username and password appear to be correct, but your system won't register, registration problems can be verified with a quick Wireshark capture either inside or outside of a NAT device. 401 unauthorized responses are expected after the first register, but if you continue to see a pattern of register messages followed by 401 responses, then it is likely that you have a bad username, password, or realm. In these cases, the realm is just your domain name, so typically sc.cfly.co for registered SIP trunks. If you're seeing register requests from your system but aren't seeing any response, then you should verify that you're trying to register the correct domain name. If you've verified the domain and are behind NAT, then ensure that your router or firewall is allowing the SIP responses back from Clearfly. A packet capture outside of the NAT device may be useful to determine if you're even receiving our responses. If you're registered, but inbound calls aren't working, you should verify in the Clearfly portal that your system is responding to options messages. If not, this is another scenario in which a capture on the WAN interface might be useful to determine if you're receiving the options messages. I want to quickly review the SIP registration process for those that aren't familiar with it so that you know what to expect when you see a packet capture or signaling logs for a registered SIP trunk. A lot of people are thrown off by the 401 unauthorized response, but it's a necessary part of the signaling flow for registered trunks. To begin with, a SIP endpoint, in this case a phone system, will simply send a register message in which the from and to headers are formatted as your username at sc.cfly.co. Clearfly's switch then responds with a 401 unauthorized message. This message contains a www authenticate header that contains a nonce value. This value is generated for each new request and will be part of the authentication response so that a bad actor can't capture a register packet and then resend or replay it later. Once an endpoint receives a 401 with a nonce, it has enough information to authenticate. To do this, it takes various values such as the username, password, the realm, the nonce from the 401, the actual method, a cnonce value that it generates, as well as a few more values, and then generates a hash. This is a standardized, deterministic operation, so when it sends a register message with the hash value, Clearfly's switch is able to use the same information to generate its own hash and then compare it with the received hash. This method of comparing generated hashes, which, unlike encryption, are one-way mathematical functions that can't be reversed, ensures that authentication can happen without a user's password ever being transmitted across the network. If the comparison is successful, Clearfly will respond with a 200 OK, and registration is now complete. If it is not successful, Clearfly will respond with a 401 so that the phone system can reattempt authorization. For registered SIP trunks, this authentication flow can technically take place in response to any request from a customer's phone system, although you'll likely only see it for new register and invite transactions. So what can you do if you see a recurring loop of register and 401 unauthorized messages? Verify your password, of course. And the Clearfly portal will give you all of the information you need to verify your trunks. The voice group view in the Clearfly portal provides a good way to verify that your configuration and Clearfly's configuration match up. You can verify the number of concurrent call sessions, any phone numbers assigned to the voice group, and you can verify your trunking parameters, including your username and password. For static trunks, you can verify that the IP address and port that Clearfly has on file matches the public IP address and signaling port of your phone system. Note that the numbers and the labels next to the tabs indicate any open voice group orders, open related LNP or telephone number orders, or open tickets on the voice group. Something really cool about the Clearfly portal, though, is the real-time switch information that's available to you at the click of a button. The Clearfly portal allows you to view and update certain values from our voice switch in real time. This means that what you see on this page reflects the current state of the switch to the second, and anything you do on this page is applied immediately to the switch. For instance, you can view alarms if there are any currently active on the customer service which would cause calls not to complete, verify that Clearfly has been provided the correct IP address information, and that the information was properly configured in the switch for static trunks, or verify username and password for registered trunks. Verify which telephone numbers are currently loaded in the switch and how many digits Clearfly is sending to the phone system. Verify and update various call forwards. Convert from registered trunks to static trunks and vice versa, and change the IP address and port of a phone system if the trunk is static. Bar and unbar international calling and adjust international calling tiers. Verify the calling number if Clearfly has an override in place. Toggle E911 test mode for multi-location trunks. Adjust the number of concurrent calls allowed for this trunk. Subscribe to and adjust your call burst settings. And for registered trunks, you can click the Registration Details button and pull detailed information about your registration from our SBC. Of particular relevance from a troubleshooting perspective are the registration, status, and first alarm fields. Basically, if a service is active, shows a registered IP address, and has no alarms, our switch believes everything is working as expected on the trunk. Based upon feedback we've received in the past, I want to add a few quick notes about the Clearfly portal. First, if a label has a dotted underline, you can click it for context-sensitive help. Second, if a trunk is not registered, the status will be activating, and the first alarm column will be pretty self-explanatory. You will also find that no registration details will be displayed when you click the button to load them. Instead, you'll get a message saying that no registration information is available. Third, if a trunk, registered or static, is not responding to SIP options messages, it will be noted in the first alarm field. And, finally, the last failure cause can help troubleshoot transient issues, such as maximum call appearances reached if you've maxed out your subscribed call sessions. Okay, we're feeling confident with the portal, Wireshark, one-way audio issues, private IP issues, and SIP registration flows, so now we'll run through some miscellaneous other problems and questions. We often receive reports of repeated phantom calls, or calls on which a customer's phones ring, but nobody is there when they answer. This can be the result of unauthorized signaling attempts to the customer's phone system. Possible fixes, assuming there are no remote IP phones or nomadic users, are to 1. Check the security settings on the phone system. If possible, don't allow responses to SIP requests from unconfigured peers. 2. Disable any unused transport protocols if possible. For example, if you're not using TCP signaling, disable it. And 3. If the phone system doesn't support filtering, apply a filter on an upstream router or firewall to ensure that SIP signaling from unknown sources can't reach the phone system. Please note that Clearfly's voice traffic will always originate from 208.85.62.0/24, and we currently only utilize UDP as the transport protocol. Another issue we commonly address is that of audio quality, so I want to quickly touch on a few QoS related points here. First, a definition. What is quality of service, or QoS? QoS is essentially the preference of one class of traffic to the detriment of another. For example, a certain QoS policy may specify that voice traffic should take precedence over a YouTube video. Depending upon the bandwidth available, the quality of the YouTube video may suffer as a result of this preference for voice traffic. Second, QoS usually only matters if a link is congested. It may be possible to have a perfectly clean last mile link to a customer site, but then end up experiencing jitter or packet loss further upstream between the customer's location and Clearfly's network. This type of issue is usually transient and due to traffic reroutes after link failures, but if a carrier supports QoS on their core links, the VoIP traffic should take priority over best effort traffic. Third, QoS policies are unidirectional. That is, separate policies may be applied for upload traffic versus download traffic. You may have a router at a customer site that is perfectly capable of prioritizing your voice traffic in the upstream direction, and this can help guarantee outbound traffic from the site, but it has no bearing on whether your ISP is prioritizing download traffic to the site. This is an excellent example of why detailed call experience notes are so important when troubleshooting. If a customer can hear a caller just fine, but the person calling in from the PSTN is hearing garbled audio, chances are very good that there is some upload congestion somewhere along the path, and usually it's right at the customer site. This is another instance in which coordinated capture can prove very useful. If a capture at the customer site shows no packet loss or jitter in one RTP stream, but a capture on Clearfly's network shows, for example, 2% packet loss and 75 milliseconds of jitter, then it's time to dig into the customer's connection to determine what may be happening in that direction. And just a quick refresher, jitter is the variation in latency between two packets. So, for example, if one packet took 20 milliseconds to reach a destination and the next packet takes 30 milliseconds to reach a destination, the jitter is 10 milliseconds between those two packets. Theoretically, latency by itself doesn't cause voice quality problems until it reaches a certain point. 150 milliseconds of round-trip latency doesn't mean that there will be voice problems if the latency is constant, which is the same thing as saying if the jitter is low. Clearfly marks all media and signaling packets as DSCP EF. We also prioritize any packets tagged with DSCP EF on all of our core, distribution, and access links. For on-net Clearfly connections, this means that if a customer wants to ensure their voice packets are prioritized on our network, they need to tag them as DSCP EF. Obviously, we can't guarantee how other ISPs will handle your voice traffic, but even for off-net systems, our recommendation is to tag all signaling and media traffic as DSCP EF. Wireshark provides a quick and easy way to verify a packet's DSCP markings. You can do this by simply expanding the IP header details. Note that this packet is in fact tagged as DSCP EF. EF stands for expedited forwarding. Another common report we receive from customers and partners alike is about high response times or packet loss when trying to ping or traceroute to Clearfly's SBC. There's information in the FAQ on Clearfly's website to this effect, but it's a common enough concern that I wanted to cover it here briefly as well. In a nutshell, our SBC is busy processing your SIP and RTP packets and will always prioritize this work over generating a response to your ping or traceroute requests. The FAQ on our site lists an alternate host you can test to that sits right next to our switch if you need more than a basic connectivity check. Beyond the basic tools we've presented so far, I want to take a moment to quickly run through a selection of the other resources you can pull from when troubleshooting your voice service. Clearfly maintains a list of phone systems we've performed interoperability testing with. Most of these were certified directly by the vendor, but you can see that some were tested directly by partners and a full vendor interop has yet to be completed. Something I'd like to point out here are the links for system-specific common issues. These notes detail problems folks have run into with these particular products and, usually a workaround or fix for the issue. This is just an example of the type of information contained within a common issues page. I'm not picking on Panasonic here. We've just had some Panasonic dealers that were willing to spend some time helping us document issues when they'd run into them. We rely on our partners for this information, and we're open to adding anything on these pages that folks are willing to contribute. Our frequently asked questions page, also available at clearfly.net, is pretty self-explanatory. As with any of the reference material on our website, we're open to suggestions. Clearfly's knowledge base entries are articles that we've written to respond to questions that may deserve more detailed answers than those you typically see in the FAQ. Again, if there's something you'd like to see in writing or explained in more detail, just let us know. Sometimes it would be useful to be able to easily share a capture with other members of your team or with the manufacturer. Cloudshark.org is a subscription site that you can upload captures to and which provides incredibly useful annotation and collaboration tools, as well as the built-in ability to decode the G.711, G.729, G.722, and GSM codecs without messing with any of the clunky Wireshark add-ons. For sticky registration problems in which you're fairly sure of your username and password and suspect that something else may be wrong with your phone system config, Clearfly has published a free, open source, and secure SIP authentication test tool to verify that your phone system is generating its hash correctly. To use the tool, simply browse to sipauth.clearfly.net, select the SIP method, usually register or invite, paste in the auth header out of your packet capture or other diagnostics, enter your password, and click Evaluate. This tool will then generate a hash and compare it to the information you provided to tell you whether or not your hash is valid. This all happens locally in your browser and no information is transmitted across the internet. And last, but certainly not least, I'd like to mention the SIP School. I first ran into these folks a few years ago and have been very impressed with their material and their responsiveness. The SIP School offers several online, self-paced, fully interactive SIP courses, both for sales and technical folks. The training starts at 0 and works its way through a comprehensive list of topics relevant to SIP provisioning, operation, and troubleshooting. If you'd like, you can even pursue a SIP School Certified Associate or SSCA certification. This is an industry-recognized, TIA-endorsed certification that demonstrates a thorough understanding of all aspects of SIP. And that's a wrap for this presentation. Please check out our other training videos in the Clearfly portal, and don't hesitate to contact us if you have any questions or comments, or if you want to report any errata. Additionally, if there are any topics that you think would benefit from a live training session or a new training video, just shoot an email to your channel account manager and we'll add it to our list. Thanks for watching, and good luck on your future installs.